All right, hey everyone, welcome back. So I'll get started as I'm already a little bit late. Okay, and if you have any questions, please interrupt me, all right? As always, I'll start with the review of yesterday, what we talked about. So, okay, we talked about the RG formalism. Okay, it's basically we vary the energy scale and analyze how the coupling constants change, right? And we showed them in various phase diagrams. Like for example, this is the uniaxial magnet. We have various fixed points. And if you start at any point, any given point, with some external magnetic field, H, and some temperature T, it will eventually flow one of these fixed points. Okay. And we said that we do not generally know how to find the fixed points. In fact, we don't know how to find the phase diagram in general, because these are usually strongly coupled, like there are regions with strong coupling, and we don't know how to solve them. We can write down the microscopic theory or pattern integral, but we cannot do the actual computation. Okay, so most of the time these are like schematic things that we know. They may change future information. Okay, but one common approach is we start around the Gaussian fixed point, because the Gaussian fixed points, this guy describes the free field theories with which we can work. Like this is something we can work with. And then around the Gaussian fixed point, we look around that region and try to find new fixed points. And in fact, we argued that this is exactly how Wilson and Fisher find their famous fixed point here. This theory is for a scalar in d minus 4 epsilon dimensions, so 4 minus epsilon dimensions, right? So we argued that if epsilon is 0, this Wilson-Fisher point is actually on top of the Gaussian fixed point. So it's actually free, which is why if d is equal to 4, everything is great, we can work. Now, if d is like, let's say 3, then this is too far away, we don't know how to do the computation. But we say, okay, let's start with 4 minus epsilon, where this fixed point is very close to the Gaussian fixed point. So we can do, we can work with the Gaussian fixed point information to poke around this fixed point. Then at the end, we take epsilon to 1. This is called epsilon expansion. Okay. Another similar fixed point is actually it's called Banks-Zaks fixed point. We didn't really talk about this yesterday, but that's important. So I'll be talking about that today. So this is now a little bit less of a review, more of a new content, but anyway. In the Banks-Zaks fixed point, so we have one coupling coefficient G, and it's in this Lagrangian. So we consider a bunch of massless fermions, which interact with a gauge interaction, SU and C. So we have a color index NC, it's arbitrary, and we have the flavor index NF. So we have the flavor group and the color group, and this is the general Lagrangian, and this G is the coupling constant, and we try to find how the system behaves at IR for various values of G. Okay, and when they did the computation, Banks and Zaks, they found that there can be a fixed point to which we can flow from the Gaussian fixed point. And that's famously called Banks-Zaks fixed point. And at that fixed point, we expect a CFT to leave. So in short, for fermions with a gauge theory, in general, a gauge theory with massless fermions, we expect so-called conformal window where they will flow to this fixed point, which will be described by a CFT. Okay. So let's try to understand this Banks-Zaks fixed point. To do this, I will define something called beta function. It's very famous in these RG computations. We don't even know much about this, but it will be helpful. So it's basically defined as this function. This G is like the coupling coefficient. It depends on the energy scale lambda. And I take the derivative of G with respect to log lambda. Why log? Because basically lambda changes like, we can take lambda to be lambda prime is equal to E minus lambda, because lambda prime needs to be positive, and e to the some power is always positive. And if L is greater than 0, that means lambda prime is less than lambda. So energy scale is decreasing, we are going to IR. Or the other way around, we are going to UV. Okay. So that's how we can define. And conveniently, by convention, we define this beta function like this. Okay, good. Now, what people do in literature is to analyze beta functions to determine the scale dependence of the coupling constants. Now, take this guy, right? Take bg to the here, d log lambda here, it becomes like this, and integrate it, right, from, let's say, initial energy scale to final energy scale with gi to gf, right? And if the final energy scale is given like this for some parameter L, then we get this equation, this star equation. So this relates coupling constants at different energy scales. Good. Now, this is very hard to solve. We cannot generally solve this, right? Beta function can be quite complicated. However, around the free theory, we can compute this beta function order by order in terms of small g, okay? In fact, this is how people do this. Like they use Feynman diagrams to compute order by order the C0, C1, C2, etc. It's a very complicated procedure, but the end result is actually minimal. It's only true around the Gaussian fixed point. Like you only look around Gaussian fixed point. If there's like a very complicated fixed point somewhere else, this really doesn't work. Okay, it's a tedious procedure, but it does work. And but instead, like we won't be bothering with this. Instead, let's consider this formula again, the start formula. But take GF to be very close to GI, just an infinitesimal change. Okay, for instance, infinitesimal change here. So this integration is basically this thing, this quantity, is minus delta L. So this is the result. That means if beta function is positive, then decreasing the length scale, like going to IR, decreases G. Okay, so if beta function is positive, that means G is an irrelevant coupling constant. You may remember we discussed relevant and irrelevant directions, coupling constants. That means that, let's say, G is equal to 0 is the fixed point, right? And I move it away a little bit. I took GI like a little bit away from fixed point. It's very small, but positive. But then delta G is negative. It takes it back to the fixed point if beta function is positive. So positive beta function means that coupling constant will flow back to the fixed point under RG transformation. So it will not go away from the fixed point. So we do not need to tune it. In contrast, if beta function is negative, that means G is a relevant direction as we go to IR. And if it is a little bit away from the fixed point, it will move further and further away from the fixed point. So we need to tune it externally if we want to stay at the fixed point. Okay. So let's get back to the, are there any questions so far? Is this clear what we are doing, like this beta function? Again, it's not really necessary, but it's a very relevant thing in this business. So at least you need to have heard of it, which is why I'm going over it. It's not like we will be doing any actual computation with that, but please interrupt me if you find anything confusing. Okay. All right, let's go back to the gauge theory with Masters fermions. This was the Lagrangian, right? Now, people have computed this beta function. Okay, so it's like this. And as I said, if this parameter A is here, if it's negative, then G becomes irrelevant. If it's positive, then G becomes relevant. Now, here is the thing. It's computed to be like this. Okay, now this factor, it's not important, but it's something positive. What's important is this factor. So if NF is too small compared to NC, then A will be positive. So G will be a relevant direction. But if NF is too high compared to NC, then G will become irrelevant direction. So the interaction in the gauge interaction is relevant or irrelevant depending on the ratio of NF, the flavor group, and NC. Like just to remind you, we had SUNF flavor group and SUNC color group. If you don't know what the flavor and color groups mean, basically color group means number of gluons and flavor group means number of quarks, basically. So in the theory, depending on the ratio of number of gluons to number of quarks, if this ratio is too high, it will be different. If this ratio is higher than 11/2, it will be different. Too low, it will be different again. Okay. Now, again, if this ratio is like this, then G is an irrelevant direction. So we flow to free theory in IR. Okay, so because basically it goes back to the Gaussian fixed point, which is free theory. And it's a free theory, so there is no interestance yet. On the other hand, if this ratio is less than 11/2, well, there are two cases. Certainly, it will be interacting theory as we go to IR, okay, because it won't be going back to the Gaussian fixed point, because we said this isn't a relevant reaction. It will flow away from the Gaussian fixed point. Now, it may go to a new fixed point, which may be at infinity or not. And depending on the situation, we have two cases. Now, there is a critical ratio, which we don't know. It's an active area of research now. People are trying to find what this number is. So it's currently not known. There are some like results by lattice simulations, other stuff, etc. But they don't really converge well. So different people claim different numbers. But the thing is, if this ratio is below some critical ratio, then in the IR, the chiral symmetry gets broken. A scale is dynamically generated, and we don't get conformal invariance. But if this ratio is just below this number, but above the critical number, then we will flow to a conformal phase. So like if QCD had just the correct number of flavor and color groups, then it would become conformal at IR, for example. Yeah, as I said, if NF is too low, we dynamically generate a scale, no CFT. If it is too high, then we can get a CFT, which is the back-to-back fixed point. Okay, that's CFT. And this ratio, this region, this interval is called conformal window. So there's a window of opportunity. there's a window of interval in which we can get conformal invariance. Okay, again, what is this critical NF? No one knows. And we can ask, where is the back-to-back fixed point, like in the phase diagram? Now, if you remember, this was the beta function. Are there any questions, by the way, about this?
I actually have, I tried to ask a minute ago, but I think I had a problem with the microphone. Oh. As I remember from yesterday, we didn't actually talk a lot about marginal operators. And in this case, we aren't actually talking about, my question is, what if this flavor number versus divided by the color number is exactly equal to 11/2? Like you would get a zero beta function.
The main reason I don't talk about marginal operators is because these computations are done perturbatively, order by order. Okay, so we don't know the exact results anyway. And if you find an operator, let's say at one loop level to be marginal, you expect that it will probably be either relevant or irrelevant at two loop calculations.
I see.
So as you keep doing calculations, marginal operators will not probably remain marginal.
But what if it did, like, I didn't actually understand what physical significance it has for an operator to be marginal. Like, I can see the relevance of relevant operators.
Okay, I guess I can okay, so let me just, okay, how about this? Let's see, this is energy and relevance of an operator. And when I say relevance, I mean like not the technical term relevance, or let me just say importance. Okay, importance of an operator. Okay, now it may be like this, it may be like this, or it may be like this. Okay, now this is relevant operator. It becomes more and more important at low energies, but its importance diminishes at high energies. This is an irrelevant operator. Like if you're an irrelevant operator, your theory is non-renormalizable, because as you go to higher energies, it will become very important. It will break the theory. But at IR, at these regions, you can basically ignore it. And this is the marginal operator. It doesn't break the theory. It doesn't diverge at UV or IR. It can be there. There is no problem. So presence of irrelevant operators make your theory UV unsafe. It's UV unsafe, meaning that it's probably non-renormalizable, because at high energies, that term just diverge. Having a relevant term means it's IR unsafe in the sense that your theory will become strongly coupled. Like QCD, for example. We don't know how to deal with QCD at low energies because it has this relevant operator. Okay. So it's probably like probably confined. And if you have a marginal operator, it's like, it's great, marginal. For instance, stress tensor, T mu, it's always there, no problem. It's important. It doesn't diverge anywhere. It doesn't break your theory, etc. So this is like the schematic view. Don't take this too seriously.
Okay,
as I said, because you need to really
it makes
solve
sense.
this. Sorry?
Now it makes sense.
Okay.
I know this is just schematic, but yeah, okay.
Yeah. Like
so it seems like if you only, like, by chance, you had a theory which only had marginal operators, everything would be fantastic. Like, would you be able to create such a toy model, like, with only marginal operators?
Yeah, the thing about this is that as we have, I taught this yesterday at the very end, but I will repeat it today. The scale dimensions are supposed to get contributions from other operators in the theory. Like if you have one operator O1, let's see. Okay, let's say I have an operator O1 in CFD. It has some scaling dimension, right? So I need this to be D for it to be marginal. Its scaling dimension needs to be D. If it is less than D, it's relevant. If it is greater than D, it's irrelevant, right? If I wanted, it needs to be D. But the problem is, if there's another operator O2 in the spectrum, it will make a contribution. Like the existence of O2 will make a contribution to this scaling dimension, delta O1.
Yeah, this is like,
and but here's the problem though. There are infinitely many operators in CFD.
That's true, yes.
They're not finitely many. Like if it was finitely many, you would argue, oh, let me tune all of them. Like maybe you can, I don't know, like this is, yeah, this is not really, again, like this whole discussion is generically true for any theory, not necessarily CFDs. So like around the fixed point, you can write down a scaling dimension for any operator, mass dimension for any operator, like in any QFD, which is why we do it all the time in perturbation theory, because we are around the Gaussian fixed point. But at the end of the day, yeah, it's just too many unknowns.
I see. Okay, thank you, John.
Okay, so where were we? Another question? Okay, so we said we don't know this critical value of NF, and we asked that could be the Banks-X fixed point, right? And okay, we said, look, this is the beta function we have. It needs to be 0 at fixed point because it gives you the variation of the coupling constant with respect to energy. At fixed point, it should be invariant. So you look for the zeros of this, like the trivial zero is G is equal to 0. That is the Gaussian fixed point. And there's another fixed point here, if G is root square A over B. Now, if you have the conformal window, then indeed at that value, you have the Banks-X fixed point. Okay, so there is a flow to Banks-X fixed point from the Gaussian fixed point. So if you start around here, you will go to here and stay there. And that is the conformal window. You have a CFD living here. Okay, that's the good thing. And this value is only true up to this order because this beta function is not the full answer. It's just like it's computed by order perturbatively. Like that may be like G to the 7 terms, G to the 9 terms, G to the 11, which you can compute order by order. Then this value will change. So this is this value at this order. Okay, because we don't know how we can compute this otherwise. Good. So this is the conformal window. I have this fixed point, and the phase diagram is a one-dimensional phase diagram because there's only one coupling constant, but this is how it behaves. Now, if on the other hand, NF is too small, let's take NF to be 0, just a gauge theory. There is no fermions, for example. Then that theory is confined in there. When I say confined, that means we don't get to see the color quantum number in nature. Like, you know, in the ordinary QCD, the gluons have different colors, so-called colors, red, green, blue, whatever. But you don't observe them. You only observe color neutral particles, right? Like hadrons, mesons, etc. And that's confinement. And this is indeed the case if NF over NC is below the critical ratio. And in that case, I no longer have Banks-X fixed point. And Gaussian fixed point is again unstable. Like if I'm, like there's a flow away from it, right? I go to another fixed point. We don't know where, possibly at infinity, right? And there is chiral breaking. There is a mass generation. And since there is mass there, the theory is actually topological. Like this fixed point is topological because the correlation length would become 0 at IR. Okay, so it wouldn't be infinite. And last case, if, okay, this was like the one case, the other case, and the last possible case is if NF is too high. In that case, Gaussian fixed point is the stable one. The flow is towards the Gaussian fixed point, right? Now, G is an irrelevant direction. This is just like QED in the sense that you can just expand around the Gaussian fixed point. You can just do the perturbation theory, which will be fine. Like think about QED, like the quantum aerodynamics. We can expand everyday stuff by using QED because the Gaussian fixed point is a stable fixed point. So we can just use perturbation theory around it. No problem. We don't need to tune anything. In contrast, in QCD, you need to tune it. Okay. Does it make sense? Okay, great then. So this was like a review plus some more stuff about Banks-X fixed points. Nice. So, okay. If there's no other question, let me just keep reviewing yesterday a little bit more. So we talked about dimensional counting and introduced the concept of anomalous dimension, right? So we said in the Lagrangian, I can have terms like this. There are these terms called operators. Okay, because in quantum theory, they would really be operators in the sense that I operate with them on the Hilbert space to generate states. But that detail is not important. Just take it as terminology. Okay, and they come with some coefficients which were called phenomenological constants in the statistical model theories, like, and they are called coupling constants in high energy physics in general. And I said, okay, I am doing this transformation. I am shifting lambda, the energy scale, and I'm shifting the parameter x, and this gives a relation between coupling constants at different energy, etc. And we argued that in general, we don't know how to compute this thing. It's a complicated flow, but around the fixed point, I can linearize the action of RG flow. Okay, I can do that. So Ki basically behaves like this at leading order around the fixed point, which is very useful because most of the time we are working around fixed points. Like all three theories are around Gaussian fixed point. So it's not something irrelevant. We use it all the time. And this exponent is called the mass dimension of X, which is denoted like this. Okay. And then we said that, okay, by using this equation, we can actually show that the mass dimension of the operator and coupling constant add up to D. Okay, like we got this equation. And this is how we like got this whole business of if this is bigger than this, like if the new coupling constant is bigger than the old one under RG, that means K grows with RG, so it's a relevant direction. Otherwise, it becomes an irrelevant direction. You don't need to tune it, so on and so forth, as we discussed, right? And we argued that in the case of fluids, for example, temperature and pressure are relevant directions. If you do an RG transformation, these parameters would move away from the fixed point. So we externally need to tune them to stay at the critical point. Okay. And likewise, for the uniaxial magnets, the temperature and external magnetic field need to be tuned externally because they are relevant parameters. And we also said that the fact that both uniaxial magnets and fluids, we need to tune two parameters, that fact is not coincidence. It is because these theories are both described by the same CFT, 3D Ising CFT, and it has two relevant operators, which are denoted by sigma and epsilon. All other operators are irrelevant, meaning that their mass dimension is greater than D. Okay. And any other thing, like there are some other examples in Ising University class, like some polymer solutions or some liquid mixtures, like there are some other examples as well. I listed them in my notes. In all cases, you need to tune two parameters. Okay. Now, we also talked about the apparent contradiction. Well, master dimensions are always rational functions, like this. For scalars, for example, around Gaussian fixed point, it's d minus 2 over 2. For fermions, it's d minus 1 over 2. Again, these are around Gaussian fixed point, right? And do you all remember how we derived this? Like from the kinetic term in the Lagrangian? Like we said, there is a kinetic term, d phi square, in the Lagrangian. It needs to have the scaling dimension d. So from that, it follows that phi needs to be d minus 2 over 2. Okay, so this is a free Taylor expansion. It's around the Gaussian fixed point, which is why I keep saying these are only true at the Gaussian fixed point. Now, at the critical point, though, these values would be different. So the operator actually doesn't scale with these values. It scales like this. So if you consider an operator O, if you change its argument with lambda, it scales like that. This delta O is a real number. It doesn't have to be like a rational number like this. And the difference is called the anomalous dimension. So the free, or like if it's free operator, its scaling dimension is the same as mass dimension. But in general, if it's interacting, then it gets this anomalous dimension. And computing this scaling dimension is like one of the ultimate goals of a CFD. So the conformal bootstrap program tries to find the operators in the spectrum and find their scaling dimension. And this is called CFD data, along with some other stuff that I will talk about. Then if you compute them, you can use them basically anywhere that CFD is relevant. For instance, in the case of Isinglass, like this alpha shows how the heat capacity behaves for a fluid, for example. And if you know this delta epsilon, then you immediately know alpha. And there are like many relations like this. Okay. Now, are there any questions so far? Okay, good. Now okay, so I want to talk about a little bit regarding the difference between scale and conformal invariance. I mentioned this yesterday. It won't be some, a huge discussion, but I think it's illuminating. So, okay, we all know that we can derive the stress, we all know that there's something called stress energy transfer, right? And we usually associate it, we usually derive it through Nadeau's theorem, right? We say there's a symmetry, and there's a generator of that symmetry, stress tensor, etc., etc. Also, we can derive this T mu nu from through curved spacetime action, like an action with G mu nu instead of eta mu nu through this equation, right? This is the action for the matter part, but there won't be any gravitational part because in this lectures we just talk about flat space. So this is like the full action. Take the action, take its variation, then you get the stress tensor. Okay, we can use as the definition of stress tensor. Good. Now, if the action of this form, right? Again, there is no rigid scalar or anything like that because we are doing flat space business. I'm just using this as a tool to compute the stress tensor. Then the stress tensor becomes like this, right? It's just this definition. If I apply it, it becomes like that. Good. Now, here is the problem though. Not problem, but let me just get rid of this, by the way. Oops, sorry. Good. Okay, good. So here's the thing. If we look at the mass dimension of T mu nu, then it needs to be equal to mass dimension of eta mu nu L, which is eta is just a metric. It doesn't have any. It's just 1, 1, 1, 1. There's like a minus if it is Lorentzian, but whatever. So it's the mass dimension of the Lagrangian, which is always d. So we found that T mu nu should have the mass dimension d, right? Okay, good, no problem there. But we know that classically, some operators, have some mass dimensions, and as we include quantum corrections, they may change. So we may wonder, maybe this also changes with the quantum corrections, but that's actually not the case. We can see this, for example, from the word identity. So this is basically generalization of the fact that the T mu nu is conserved. So this is like classical. Its quantum version basically says if you have T mu nu in a correlation function, x1, O, xn, actually let me just x, O, x1, O, xn, and they don't need to be same operators. Then this is equal to minus summation of I, delta functions, minus xi, delta I nu times O1, x1, On, xn. Okay, so this is the word identity, which is true at level of quantum fluctuations like in QFT. But from this, we can see that if we just take the mass dimension of both sides, right? Just take the mass dimension of, that means mass dimension of delta plus mass dimension of 2 plus mass dimension of O1, mass dimension of On is equal to mass dimension of delta D, delta function, plus mass dimension of D plus O1 plus On, right? So these cancel. And this shows that the mass dimension of T is equal to mass dimension of D-dimensional conical delta, which is D. So we see that the mass dimension of T is always D. It doesn't get quantum corrections. Okay, so we say T mu nu is a protected operator. Okay, because of the word identity, anomalous dimension of T is always 0. Doesn't get any anomalous dimension from the existence of other operators in the theory. But here is a thing though. So, okay, actually, here's the thing. I think it was called virial current, but yeah. Anyway, so the scale invariance and conformal invariance have to do with the trace of T mu nu. Okay, so if you want to understand whether a theory has conformal invariance or scale invariance, we need to check the trace of T mu nu. And if you check it, in general, the trace of T mu nu would be of the form, actually, let me say equal. It would be of the form delta rho K rho, where, actually I want to use V rho, where V is called virial current. Virial current, okay. So it's called virial current. Now, if it has this form, then we say theory is scale invariant, but not conformally invariant unless V is equal to 0. So in other words, if the trace of stress tensor is 0, then we get the full conformal invariance if it is 0. But if it is like a full divergence, then we get the scale invariance, but not conformal invariance. Now, earlier we argued that the fixed points of phase diagrams, like the fixed points, need to have scale invariance. So we may argue in general, they can be of the form T mu mu is equal to delta rho V rho. So we don't need to have conformal invariance. And it's perfect at the classical level. But take the mass dimension of this equation, right? So we have T is equal to delta plus V. We said that because of the word identity, this is always D. This is simply 1. That means V should have the mass dimension D minus 1. It looks like this also needs to be protected. Needs to be protected as well, because it shouldn't get any enormous dimension. If this equation is to be trusted at all times, even at the quantum level, that means the virial current should have a protected mass dimension. But in general, this is not really true. Like we need some Wald identity for that current, some kind of identity for that current to make it protected. Okay. So in general, we do not expect that. Like we need to have some kind of symmetry in the theory to have that. So since we don't expect that, the only solution to T mu mu is equal to delta rho V rho is done if T mu mu is equal to 0. So that means if we have scale invariance, at quantum level, then we expect conformal invariance at quantum level because of these arguments. Okay, we expect. This is not true in classical theory, because in classical theory, like we don't care about enormous dimensions, stuff like that. But in at the quantum level, if we have the scale invariance, we do have this expectation.
Soner, do you know any exception to this? I know that it's not a theorem, but I haven't seen any, to be honest.
To my knowledge, there is. Okay, so let's see. I do remember seeing some. Okay, if you give me a moment, I'll just check in my computer. I do remember. Let's see. Where was it? Not this. Was it here? Okay, yeah. In ADS, for example, I know that there are some examples in ADS. I can share that. Yeah, also like the 14 has an example. Yeah. So I know that there are some examples, like at special cases, like if the theory is non-interacting, for example, it's fine, even at quantum level. Let's say if you have a quantum theory, it can have scale invariance, but not conformal invariance if it's a free theory, because then we wouldn't get any enormous dimension. So free theories are exception in that sense. We can have that.
But that's kind of trivial, right? So
yeah, that's trivial. And there are some examples in ADS. Let me just share the name of the papers. Where are they? Okay.
Gökhan Hocam, I think I believe Polchinski had a paper about this issue. Like, does it?
Let me share this. I'm gonna share.
Yeah, I mean, the main result was you cannot prove a theorem. But what I'm asking is, I mean, I haven't seen any counterexample. So maybe, I mean, since
so I shared a paper. I think they construct some models.
Okay, I can check it.
Yeah, like it's in like curve background in a sense. So they kind of manage it. There's a rotation. So they have a boundary term at ADS which breaks the conformal invariance, but not scale invariance. So they have like a model in ADS, which is it's interacting, scale invariant, but not conformal invariant, because there's a boundary term which breaks the conformal invariance in a sense. They say like 6-dimensional field theory residing on rotating Euclid Einstein universe, something like that. And also, let's see, there was another example.
Well, we can also use the discussion hour, so
yeah, okay.
Interrupt you.
But anyway, in 2D there are examples, of course. 2D is a different case. But long story short, this is the argument. If it is non-trivial, it's interacting, we can safely expect it to be CFT. Okay, that's that. Are there any other questions? Okay, good. So how much do I have? I have half an hour. So let's start with some mathematical basics. Okay, like about conformal symmetry, conformal algebra. Actually, let me just start with conformal algebra, right? Now, for the past 3.5 days, I've been motivating CFTs. I've been like giving examples where they're relevant, etc. We may as well just talk a little bit about the mathematical background about them. So to answer conformal algebras, I actually will review the let me start with translation algebra. Okay, let's start with something simple. So translation algebra, TD, like I will stick to Euclidean signature. Everything will be true in Lorentz signature. You will just put some I's in some generators. Okay, so let's just stick to Euclidean for simplicity. You can ask me if you don't answer at some point about the translation. Okay, so translation algebra TD, it has the generators PK, and they satisfy this relation. Okay, so for an algebra, for a Lie algebra, you need to give the commutators. Okay, so if you say there are these generators, let's say X and Y are generated, you need to show us what this thing is to define the algebra. And translation algebra is basically just a Abelian algebra. It has D generators PI, and they satisfy this relation. So their differential representation. So we can say what is differential representation of PI, right? The algebra element that generates translation. So we know that the group, basically, at least connected part of the group, is e to the algebra. Okay, I am being very schematic, but this is like the connected part of the group. So we can try to find e times alpha p acted on a function x should give me phi x plus alpha, right? This is how translation should work. And I'm trying to find the differential representation for p. Now there's a very simple way to do this. We can just expand both functions for small alpha, right? 1 plus alpha p plus alpha square over 2 p square, blah, blah, blah. Phi x is equal to phi x plus alpha times d over dx phi x plus blah, blah, blah. And by just matching terms, order by order, you can immediately see that the differential representation is d over dx, right? That's kind of trivial. But I want to show this a little bit longer. Okay, so to show this in a longer sense, what I will be doing is I will be using the Fourier representation of phi x. Okay, so it's ddp over 2 pi d e to the I k dot x phi tilde p. Okay, so this is its Fourier representation. Nice. Again, for this case, it's trivial, but I still want to do that. So, and I'm trying to solve e to alpha p phi x is equal to phi alpha plus x, right? It generates translation. So that means e to, this should be k. Good. And this should be k. Okay, good. So now that means e to alpha p ddk 2 pi d e to the I k x phi tilde k is equal to ddk 2 pi d e to the I k x plus alpha phi tilde k. So we see that basically we need to solve e to alpha p e to the I k x is equal to e to the I k, e to the I k alpha e to the I k x, right? Then basically it's the same thing. You can immediately see that p needs to be d over dx. Okay. But the difference here is that these functions, e to the I k x, is actually the eigenfunction of these operator, in the sense that when p acts on e to the I k x, it doesn't mix. Okay, this is proportional to e to the I, let me call this k1, I k1x. So p does not mix mix K1 and K2, let's say. When I act on e to the ik1x with P, what I get is proportional to e to the ik1x. So this is because that guy is actually the eigenfunction of P. Okay, and what I did was like, I start with this function, I expanded it in the eigenfunctions of the translation operator, which made my job more trivial. But it was already trivial here, like I could, this is also simple, but nevertheless, this is more systematic. Is this clear? Okay, so in summary, the translation algebra TD has elements Pi with a differential with the representation delta I, and there the computation relation Pi Pj is equal to 0. Good. Now let's consider next similar example, the scaling algebra or dilation algebra. Okay, so actually let me do rotation first maybe. Did I update these in my notes? I actually don't remember whether I updated them. No, never mind, it's fine. So let's do rotation algebra first. Rotation algebra, which is denoted as SOD, right? It's the rotation algebra SOD. Let's see. Just a second. So I think I wrote them up. Let me just go myself. Yeah. So they satisfy. I'm trying to. I don't know it by memory, but MKL satisfy. Okay, I found it. Actually, let me write like this. So MAB, MCD. Yeah, there's a potential minus error I can make, which is why I was looking for it in my notes. MBC plus eta BC, DA plus eta AC, and DB plus eta BD, MAC. Okay, good. So then algebra, rotation algebra is generated by the anti-symmetric generators, and they have this commutation relation. Okay, they have this commutation relation. Now the question is, I need to find the differential representation for this operator. Okay, again, sorry.
Well, we can fix it by using the anti-symmetry, right? So the second and fourth term should carry a minus sign.
No, I ordered them so that everything is positive.
Ah, okay. Sorry, I missed it.
Yeah. Which is why I was checking my notes. I don't want to bother with any minuses. Yeah. Anyway. Okay. So yeah, as I was saying, okay, we want to find the differential representation for these generators. So I want to have something, let's say, some theta AB times MAB. It acts an operator R, a vector, and it rotates it to R prime, right? And I want to find how we can find MAB. Now, if you remember earlier, we did the Fourier transformation because the epsilon, like the I to the e to the ikx was the eigenfunction of the rotation. And it would be good if we also expand in eigenfunctions sorry, the eigenfunction of translation. So similarly, we would like to expand eigenfunctions of rotation, right? So it would be nice if we switch to spherical coordinates, right? Then we can say, okay, e to the, let's say, how to say it? Okay, let me just go alpha times some some generator acts on r theta phi, and it's rotating, let's say in the xy plane. Okay, I chose my plane, I chose my coordinate system x, y, z, such that this generator M is rotating in the xy plane. Okay, It's on changing phi. Good. Now I'm trying to find the generator M. Nice, it does rotation. So again, like similar to Fourier transform, we need to expand in the eigenfunctions, again, functions of SO. The algebra, I mean, generically, this is very complicated. Like this is related to so-called harmonic analysis, which I'll add a little bit in my notes. We can also discuss it if you like, but I'll just do a very simple case, which will be a lot easier to understand because it's very relevant. SO3, right? Now, in the case of SO3, actually the relevant functions are Wigner D functions. Wigner D functions denoted by D, J, and M prime. And if you, these details are not important. Please don't ignore them if you don't understand them. If you consider the quotient of SO3 to SO2, then this becomes the spherical harmonics. It's basically Y. Actually, I should have used L here. It's more convenient for me, the L. It becomes Y, L, M. So during this transition, I set M is equal to 0. Okay. And the nice thing is that this is actually a two-sphere, right? So that means I can basically just do my reparametrization of phi, r, theta, phi as a L from infinity. I'm expanding in terms of spherical harmonics, basically. Okay. This is same thing as doing a Fourier transformation for translation. R to the L, P to the L, M cosine theta, E to the M, M, I, M, phi, times some Fourier coefficients, L, M. Okay. So this is my general expansion. I choose this expansion because that is the eigenfunction of the rotation in the xy plane. And indeed, if we now use this relation, okay, if we use it now, we see that e to the alpha m times this thing, 0 infinity, m from minus L to L, R to L, P, L, M, cosine theta, E, and phi, times the Fourier coefficients L, M, is equal to this rotated guy, right? Which is 0 to infinity, M, L minus L, L, R to L, P, L, M, cosine theta, E to I, M, phi plus alpha, F tilde, L, M, which means e to the alpha m is equal to, sorry, hitting on e to the I m phi is equal to e to the I m alpha e to the I m phi. Okay. Oh, sorry. There are two m's now. It may be confusing. Sorry. This, okay. It may be confusing. Let me, okay. So I'm gonna use black m for the generator. This small m is just a label, okay? These small m's are just labels. They are not really, they are different m than that. Okay, I should be more careful. Let me just write it like this. Sorry. So this is, oops. It's like that. Yeah, this is better. So this is acting on that. Okay, this is the correct equation. So this is the correct equation. Sorry, yeah. So this generator, which we are trying to find its differential representation, acting on this, generates this thing. So if you just solve this, clearly it's very easy to solve. You can just expand the Taylor expansion. That means m needs to d over d phi. It's very obvious, by the way, when we solve it. Like, you know, you could have immediately said that without doing any of these. But I'm showing them because, like, for more complicated algebras, you kind of need to do this. Like, for this case, it may be very simple, but we will consider like harmonics of conformal group. We may or we may not actually. I will put them in notes, but maybe we won't have time. But That's kind of important thing to know. Now we can go back to our Cartesian coordinates as follows. X is equal to r times standard coordinates. What was it? Sine theta cos phi. Y is equal to r sine theta sine phi. And z is equal to r cos theta, right? Now by chain rule, d over d phi is equal to dx over d phi, d over dx, dy over d phi, d over dy, and dz over d phi, d over dz. Now, dx over dy is basically what? It's minus y, d over dx, plus dy over dy over d phi is x. You can check it. Yeah, times d over dy, plus this is 0. So that means phi was associated with rotation in xy plane, and the relevant generator turned out to be x del y minus y del x. So if we consider an arbitrary theta ij as rotation in xi xj plane, then the corresponding generator mij would be xi del j minus xj del I. So these are the differential representations of the generator. And indeed, you can check that if you insert them back, where was it? Back here, you can see that they are satisfied. Okay. Is there any question here about the procedure? Good, so we have seen the translation algebra, the rotation algebra, and actually we can combine them to get the Galilean algebra, right? So, okay, did I write this? I guess I didn't write them. I didn't write, right? I don't think so. Okay. Basically, yeah, okay, so the Galilean algebra is the, or Euclidean algebra actually. Euclidean algebra, ED is basically the rotation algebra, SO, D, semi-direct product, semi-direct sum translation in D dimensions. So when I say semi-direct product, that's because it's because the commutator of P and P is 0, like does not include M. Commutator of M and M is proportional to M, does not include P, right? And the commutator of P and M, which we can check, is proportional to P. Okay, so actually we can check it. Let's say Pi MKL would be something like, I don't know. Yeah, we can check it. I don't want to do it now. If you want, we can do it. It's proportional to P. So if it was 0, then we would just say they decouple into two algebras, right? If this was 0, if P and M commuted, then we would say they are independent algebras. We can write it as a sum. But since they depend on P, but only on P, in other words, the only thing that gives M is M and M. So that's 0 in the front. And we say it's semi-direct sum. Okay, it's really not that important. And yeah, I just want to tell it for reference. Now, lastly, let's consider dilation algebra. Dilation algebra. It's D1. Okay, so it has only one element, so there's no commutator or anything. But the whole point is that, let's say it's generated by the element D, right? So its action as a group should be E times, let's say, lambda to D acting on phi X should scale it to phi, let's say, E to the lambda x. Okay, so that's how we define it. It scales the parameter x. Now, I am not writing it as phi lambda x, because then for lambda negative, that would mean x goes to minus x, which would include inversions. We don't want inversions. We only want to dial scaling. Okay, so it shouldn't change the sign, which is why I am writing it like this. And then lambda can be just real numbers. Good. Now, so again, this is actually almost same thing as like rotation, the translation algebra, but for your reference, the eigenfunctions of scaling is actually given by the so-called Mellin transform. Okay, so there is the Mellin transform. You basically expand the function phi x as integral of g minus I infinity plus I infinity ds over 2 pi I x to the minus s, and like the Fourier coefficients phi s. Okay, so it's around the complex contour. These number c's depend on the locations of the poles of the function phi x. So technically, you can always find a stripe. So there's like a stripe in complex plane on which this is well defined. Okay, so you need to take in some, like there's some complexity there. You need to make sure the poles are at the correct places, like to the left of the stripe or right of the stripe. I personally don't know details that much, but yeah, you can do this basically. Okay, so if we insert this, then this relation basically means e to the lambda d integration ds over 2 pi I x to the minus s phi tilde s is equal to this thing, integration ds over 2 pi I e to the now e lambda x to minus s phi tilde s. Then we see that e to the lambda d x minus s is equal to e to the lambda s x minus s. Okay, that means d is equal to d over d log x. Okay, so it's actually x times d over dx. You can just insert it and check that.
Üzerinde eksi var. There is minus
Sorry?
sign. I think there is minus sign because it's minus to the power x.
Right, that's
E
true.
to the minus, I think.
Yeah, I get you. Yeah, you say this is minus, right? I mean, usually, like, okay, so I don't really care about the details, like, because usually you should use e to the I lambda d. Like, it depends on whether you want your generators to be Hermitian or anti-Hermitian. Like, mathematicians prefer e to the parameter, let's say like alpha times p, and take these to be real numbers, and the generator become anti-Hermitian. You know, like in physicists usually use like this, for example, that these become Hermitian, blah, blah, blah. So I didn't really care about signs and eyes most of the time, but maybe I should. Let's see. Yeah, but in this case, you're right. There should be minus sign, which looks a little bit unusual. Maybe I should define it as with a lambda sign, so with a minus sign, maybe. Was this plus? I think it was minus. I don't, yeah. Anyway, let me define it with minus sign. Okay, for simplicity. So that d is just plus x times del x. Okay. Now, here's the thing. This is in one dimension, right? But in higher dimensions, it becomes this x mu, the x mu, del mu. You can reason it as follows. In higher dimensions, if you have scaling, let's say x mu goes to e to the lambda times x mu, go to spherical coordinates, spherical. Then r goes to e to the lambda r, right? And theta remains unchanged. And then we can find that the generator is r times del r. And then you can go back to the Cartesian coordinates and d becomes x mu times del mu, okay? So this is the way to do it in higher dimensions. Okay. So in summary, we had translation, rotation, and dilation algebra. Dilation generated by delta mu, x mu delta, well, let me just use that delta A, x A delta B, x B delta A, and x A, well, it's summed over, but anyway, x A delta A, it's Euclidean. So yeah, these are like the subalgebras. And there is another algebra actually called special conformal algebra. Okay, it is, I think it's not as SCD. I am not sure how conventional this notation is. I know that these are conventional, but I don't know about this one. They also do not like general conformal as GC, but anyway. So I won't be going into this, but this is basically, I guess I can do it tomorrow, but because I only have 3 minutes left. This is basically like translation, but it is, okay, let me write like this. Translation, D and SC, D. D fixes infinity. Okay, under translation, infinity doesn't change and moves origin. In special conformal transformation, it fixes origin and moves infinity. Okay, apart from that, they're basically the same. Because special conformal transformation is basically inversion, then translation, then another inversion. Okay.
Can I ask you a question here?
Yeah.
Since we can special conformation like this, and we already know what translation and inversion is, why do we need to define a new generator at the first place?
So inversion is not an element of conformal group. It's not part of conformal group. The thing is, conjugation by inversion is an outer automorphism of conformal group in d dimensions. What it means is basically take any element of conformal group, conjugate it with inversion, the resultant thing will still be element of conformal group. But the inversion itself is not element of conformal group. This is why it's called outer automorphism. If it was itself element of conformal group, then it will be called inner automorphism. So basically, yeah, you're right. You can also extend the conformal group, include inversion, which is the case if you have parity symmetry. Like if you have a conformal, let's consider a conformal field theory, and assume you also additionally have parity symmetry, then yeah, you can consider inversion as well. But that's not guaranteed.
We don't do that in physics, I think, as far as I know.
Well, you can do it. For example, take Ising model, as we mentioned earlier. You know, Ising model. It has 2 elements, sigma and epsilon. Sigma is odd under Z2, and epsilon is even under Z2. So under Z2, under Z2. Now, if you consider correlation functions of only epsilons, you can then consider inversions because they're invariant under inversion. So your symmetry algebra enlarged from just conformal symmetry to like parity invariant conformal symmetry.
Okay, thank you.
Sure, no problem. Yeah, that's that. So yeah, tomorrow I would quickly review this special conformal algebra and maybe show what exactly it does, because these are basically it. Like these four things: translation, rotation, dilation, and special conformal generators. They are sufficient. Like they're all elements to generate conformal transformations. Okay, so knowing these four of them are sufficient. And in fact, so the conformal group in D dimensions is isomorphic to SOD plus 1, 1. So a conformal group in D dimensions is, let's say, in RD, that is isomorphic to RD plus 1, 1, which is why there is ADS CFT in the first place. Okay, because isomorphism match. This is like the basic need. I mean, this is not sufficient, but this is necessary. So we have this isomorphism at the level of algebra, at the level of group. It's like you need to take some portions, I guess. Anyhow, so you know the Poincare group. Let's say the Poincare group in a homogeneous SO group. By the way, I'm taking a few more minutes because I started late, but let's just take a few more minutes, just 2 more minutes. Like for example, 3,1, right? This is the Poincare group. Then the stabilizer subgroup of this from massive guys is like SO3. So you label particles, massive particles by SO3 representations, which is why we only have one parameter for spin, because SO3 irreps are labeled by a parameter which is half integer, like multiples of half integer, like L is 0, 1, half, 1, etc. The reason we say like a particle is spin 1, spin 2, or whatever is because the representations that we use to label particles is SO3 irreps. And this is because even though we are in 4 dimensions, this is the stabilizer subgroup. So you need to know the stabilizer subgroup to label particles or objects or operators, whatever. And we will see that in the case of conformal group in D dimensions, isomorphic to SOD plus 1, 1, the stabilizer subgroup will be SO1, 1 time SOD. And this will be labeled by delta, the scaling dimension, and this will be the usual spin. So in conformal field theory, you get spin labels, right? Like L is equal to 0, 1, etc. But you also get another label, scale dimension, which is a real number. And in fact, when you go to ADS, this would go to ordinate spin, and this will relate to mass. But yeah, that's true forever. So, okay. So to answer all this, we need to understand these 4 algebras: translation, rotation, dilation, and special conformal transformations. Okay, I already took like 4 minutes, so I don't want to take any more. Are there any questions? Okay, now I'll stop recording.